And this discussion is going to correspond to section 1015 in your textbook, where they go through a typical KSP calculation to determine the molar solubility of calcium carbonate in a neutral aqueous solution. And so remember that when we say solubility or molar solubility for calcium carbonate, that's going to be the same number as the equilibrium concentration of calcium in the water, like we talked about in class on Wednesday. So if we're asked at a first pass, what is the solubility of calcium carbonate in neutral aqueous solutions, and we're not told to consider any other equilibrium, we write out the reaction that would describe the solubility of calcium carbonate, which, as for any water-insoluble ionic compound, is calcium carbonate solid ionizes in water to give calcium 2+ and carbonate 2- in an equilibrium fashion. We need to write the KSP expression for this reaction. Calcium carbonate as a pure solid doesn't appear in our KSP, so the KSP expression is the concentration of the calcium ion times the equilibrium concentration of the carbonate ion must be equal to the KSP value, 4.16 times 10 to the negative 9th at room temperature. If we treat this with an ice table, we don't have to do anything with the calcium carbonate, so we leave all the calcium carbonate fields in the table blank. The initial concentration of calcium 2+ is going to be 0 because none of the calcium carbonate has dissolved yet. Same for the carbonate. The change in concentration is going to be plus X molar and plus X molar for each species, so the equilibrium concentration should be X and X. If we plug the X's in for the equilibrium concentration of each ion in the KSP expression, we get the relationship X squared is equal to 4.6 times 10 to the negative 9th. So the molar solubility S for calcium carbonate will be the same as the concentration of the calcium ion at equilibrium X. And we can find the molar solubility of calcium carbonate by evaluating the KSP expression and solving for X. So the molar solubility of calcium carbonate is going to be the square root of 4.6 times 10 to the negative 9th. The calcium concentration at equilibrium is therefore 6.9 times 10 to the negative 5th molar. So this would be our first pass at trying to understand how much of the coral's exoskeleton is going to dissolve under typical aqueous conditions. Here, we're assuming that the dissolution of calcium carbonate is disconnected from any other related equilibrium, and we're just saying if the coral exoskeleton was left alone in water, we can use a KSP calculation to determine about how much calcium would dissolve into the water. This calculation is not really suitable for the whole ocean. It's really too simple to describe the problem with our coral reef. But if we're talking about the fundamental chemical reaction that describes the breakdown of the coral exoskeleton at any given time, this would be the simplest chemical reaction that would describe how the coral exoskeleton could break down. It's not really suitable for the ocean though, and it's not even really suitable for a controlled lab situation because it doesn't reflect some of the complexity of our system. The big key is that this is not really capturing what's happening to the coral's exoskeleton, because while calcium 2+ is not an acidic cation, it's not going to go on to further react with the water in any other meaningful equilibrium way. We know that carbonate, CO3 2-, is a weak basic anion. And so when the calcium carbonate dissolves, it releases this unreactive cation, but it also releases this basic anion. And the basic anion can go on to react with the water and establish other equilibria that are going to then affect the concentration of both calcium and carbonate through Le Chatelier's principle. Le Chatelier's principle, remember, says that if you have a system at equilibrium and the concentration of the reactants or the products changes, the equilibrium will adjust the equilibrium system will adjust to reestablish its equilibrium. And a simple shorthand for that rule was if you remove a product from the system, if you decrease the concentration of a product, like carbonate goes on to react with water in a new chemical reaction, decreasing the concentration of carbonate, the equilibrium system will adjust to make more products. And so in order to really understand what's happening with the coral, we have to take another step, and ultimately on Monday we're going to have to take another couple steps after that. But the next step is, this doesn't capture all the complexity of the system because we know that carbonate is going to go on and react with water because it's a base. It's going to start taking protons from water, and it's going to change the pH of the water. It's going to liberate hydroxide in a new chemical reaction. And so if we really want to understand how soluble the coral's exoskeleton is going to be, we need not just one equilibrium reaction, but we need a couple of equilibrium reactions to describe the chemical complexity of the whole system. And this is where our life gets hard in terms of predicting what's going to happen to the coral, but you have the skills to deal with it. We just have to start you thinking about a process for how we can use those skills to address the problem.